All right, class, let's go with it. This is the day before the exam. Give you guys answer any homework questions, first of all. Second of all is maybe give you time to finish up homework or time to do homework. Third of all is if you do have that sort of homework, like, I just want to know the answer to this, okay? I don't mind you guys emailing me and saying, Mr. NGO, how do you do this? I'm not sure about this one. We're good? So between now and, yeah, if you have another question or so, okay? So this could either be a very short class and you guys give you time for homework. This could be a long class where we're just going over a whole bunch of homework questions. Up to you guys, we're good? So whatever you think. I do want to just go over the study guide itself, send it to you guys, what, right before lunch last time or something? Then I entered into my meetings. So the study guide, there's a non-calculator portion and there's a calculator portion. And then as I was looking at it, 1.5 sort of dominates this quite a bit as far as instructions, because 1.5 is very delineated, right? You got to do this for the exponential function. You got to do this for the, right? And so 1, 2, 3, 4, 5, 6, 7, 8, right? These 8 questions here come from 1.5. So it's not like this is just going to be one question. We good? I'm thinking like maybe like 3 questions here, right? Looking at a graph, this should be fairly easy as well, right? Look at a graph, and say, oh, that's 3, or that's does not exist. The only thing that I can probably do, let's see, evaluate techniques. Remember those techniques that you guys have? That was what, 2.4?
Are those on the cheat or the sheet we get in the class?
The formula sheet? Yeah. This one I'm kind of debating here. The proof for this one was more of a geometric kind of proof. This one is more of the algebraic proof. I think I'm going to go with this one here. In fact, let's just go this. Can you redo this proof for me? Okay.
Wait, so we're gonna have to use that tangent thing with the...
No, because this one's just straight. It's algebra. You do this, then you do this, then this equals this equals this, and there you go.
Oh, because you have to be on the top. So that's what you
Good, yeah, I think that's the one. Yeah, that works. Okay. To do stated which discontinuity is presented, graph or equation. That should be pretty easy. That's just kind of looking at a graph and saying, oh yeah, that's this, right? Jump continuity, right? Infinite continuity. Anybody know the next one? Is it jump?
Oh, there's one more where it's just like 1 point out.
Removable discontinuity. Okay, cool. And then use the precise definition limit to prove a linear function. So we're just going to go with that difficulty. That's it with that one. Okay, calculator portion, change of base formula for ln or some log function.
So it's just going to be like more harder numbers.
Correct. Yeah, just good. And then these guys are just going to be solve an exponential or logarithmic equation, give answers to the nearest hundredth or something like that.
Do we have change of base on the non-calculator also?
Yes, we do. This one right here. That should work out nicely. And then this one does not work out nicely.
Why would you need to use change of base on non-calculator with any numbers? So this is like we just do it.
Say again.
I understand using change of base when you have a calculator that won't do base like 3 or something. But why would you do it by hand if you could just do it normally? Like, why would you change it to base 10 or ln?
Sure.
Or is it just an exercise to make sure we know how to do it?
Exercise to know it, and then at the same time, sometimes you do, very rarely in math, you're like, oh, I can just change the base here. And then that works out very rarely. When numbers are, let's say you have a log of 25 on top, and then you have log of 5 on the bottom, then you're like, oh, that's just 2. Right? Because if you do log change of base formula, that's going to be log of base 5 of 25, which is 2. All right, let me write it down. So something like this right here, which you eventually get used to both forms here. This is a log base 10, correct?
Yeah.
And so you have that on top, and then you're going to go with that on the bottom. So then you kind of, as I'm thinking about it, you probably do it more in reverse than the forward way about it. You realize, oh, hold on, that's just going to be log base 5 of 25, which really just 2. I'm just kind of thinking by hand. How did I have ever done it? I've done it this way. I went the backwards way in order to simplify something. Okay. With that said, you guys talk to me here. Any homework questions from the textbook, or do you guys want to have just time to do homework? What would be most useful for you guys? Okay, okay. You know where you left off, so you can continue? Okay. So I have one book here that you guys can use. That's fine. Then I can also project. So let's go around. Kate, what do you say? Just time for homework or homework questions? What do you need? Okay. Say it. Same. Okay. And Sadie?
I also have a laptop.
I can also help individually as I walk around as you guys are doing it. So.
But I have a significant amount of questions.
Okay.
Or
Okay.
ones that I got wrong because I haven't corrected them all yet. But
Okay.
I graded all my homework.
Let's do this here. You haven't graded your homework though, right?
I did grade.
You did.
It.
Okay.
I just have the
You
ones
have
I got wrong.
questions. Let's do this here, just so for the video as well. You guys take the time for homework. Don't need to listen to me. We good? I'm going to take Sadie's questions just so we have a video recording off of it. Okay, that would make sense the most.
Maybe can I get on my phone so I can look at the problems?
Say again?
Maybe can I get on my phone?
Yeah,
so I can look at the
absolutely.
problems?
Go for it. And then, okay, I think that's the most. Okay, you said you had a laptop with you or something else you can look at? Go for it. Yep. Yeah, bring out your laptop, bring out your phone, whatever you have to use it. I did find an app that actually has the book itself.
Yeah, it's like the OpenStack.
There's an OpenStax version, and there's this, which I thought was an easier. Let's see what this is.
I just have like the book and then I have
I have this one. I'm just trying to find. It's an orange one. It says CALC Volume 1 on the bottom there.
Wait, so is it like, because my one, it's with the OpenStax, I guess, app. Can you see it?
Yeah,
It's just like has the whole book.
Okay, has the book.
I don't know,
Okay,
but-
perfect. Yeah, this one it was just the book itself. It's like a.
Oh, just, so this one I could get other books on this, but I don't.
Yeah, you can get all the other OpenStax books if you want. This one was just. It's a PDF book builder program, and they have one of them on there. So whichever one.
Okay.
Okay, who would like a physical textbook in their hand? Okay, sounds good. Physical textbook. Hey, do you look over there? Okay. So, taking homework questions now. 2.5. And which problem again?
It's 181. I think I would get how to do it if I knew what I was supposed to be doing.
Sure, yeah. Sorry, give me the problem again.
181.
181. Okay.
So
Sorry, 181.
is less than X.
Okay, this one moves from 1 to 1 to 1. Okay, 181. Okay, this one here. Let me write it in. Is equal to 2 less than 0.5.
So if I draw my little
Right, the
graph.
appropriate epsilon delta on the following graph, the function f satisfies the function.
If I draw my little graph, then I can see that it would.
The graph looks like this, correct?
That's a curve.
It's a curve.
And then 2 is 2. The limit of f(x) is x goes to 2 is 2.
Yep. 1, 2 here, right? Boom. And then 2 there.
so I got this right here. Just want to make sure, and I got this right here. So fx goes to 2, and say it. Go ahead.
So it's the 0.5 above on the graph form, right?
0.5 above, 0.5 below.
E and then, so
There.
since I don't have the actual or fx, I don't know how I can solve it or do it. I just know because I only have the graph. I don't have the actual function.
1.5, 2.5 is our values to work with here. Okay, the following graph, the function f satisfies following exercise determine the value of delta greater than 0 that satisfies each state. I think what they want to just make you realize, and I'm not sure if it's a full answer for it here, but I think that you notice it's a curve, correct?
Yeah, so it's like going up in a greater.
So I want you to realize if you plot x squared, let's just plot x squared in here. X squared would go this way, right?
Yeah.
2, you would be all the way up at 4, right? But this one's less than x squared, right? It's going up slower. And then we have this little guy to deal with right over here. So just kind of putting those two components in your mind. It's a curve. So with a curve, it has to be less than 0.5.
Yes.
Does that make sense?
Yes.
And then, if you realize this is a curve, it's not as fast as x squared. So then on a calculator, just kind of punch this in. Take a square root of 0.5. Right, because the square root would get you back to the x values themselves, right? Does that make sense? Sure. Let's see if this. It's a little bit more of an abstract problem. It's not so much here's the number and you're done. It is.
Why would it be?
Sure.
Why would the x values be the square root, or why would you take the square root?
Sure. So here's my if I were to have an x squared function, right? It would go up like this.
Yeah.
It would be already going up faster than this one.
Yes.
So that means that this function here, it's a curve, right? Because it's a curve, but it's going up slower value than x squared. Good. So so that means the range for this one would be more broad, right, than the range for this one. Does that make sense? Let's see.
Yes.
Right?
Because it's going over more, so it's going to have a wider, right? Yeah, I think I see it.
Right. So I'm thinking.
So I know it's going to be less than 0.5, but how do I figure out what?
So let me check something over
I
here.
think I know the answer. I think we looked at the answer. But 0.25 because
So I take a square root of.
square root of 0.5 is 0.7. The answer is delta is less than 1/4. Less than or equal to 1/4.
1/4.
Or 0.25.
Okay. So it takes half of that here.
I think if I draw my picture and try to draw it really accurately, it looks like that's what it is. If I look.
Oh, okay.
But I don't know how I would actually know that.
Yeah. No. As I'm thinking about it more as well, I'm thinking the x squared form won't work. I almost want to say maybe it is. Maybe it's just looking at because you don't know the function. That's the problem. There's no function value there. So I'm thinking about it too here. I'm thinking maybe it is just looking at the diagram and bringing down the values there. It is, yeah. So visually, and that's why having these recordings, because I'm sure Enrique and Christopher might have the same questions here. So for 181, it seems like, from what I can get, because you're not given a function, you're just given the fact that it's a curve. I think it's just a visually, you look it down, you're trying to pinpoint where that would be. And yeah, the furthest seems like you're going is 0.25. And then understand, that's just delta, right? You could squeeze delta lower and lower if you like, right? So you could squeeze down delta, because delta is the interior interval of what you
So it's like,
have, right? So if you put delta is less than 0.1, you're still in the curve.
yeah, because, so, is it kind of like, if you're trying to find the limits, you're trying to get close to something, and I say, okay, you have to be between this and this, right, on the y-axis, and you say, oh, I can make that smaller.
Yeah.
So every time you make it smaller, and then I can make delta smaller. So
Absolutely.
is that what the definition means? Okay.
That is perfect.
Okay.
And so visually, I think that's what they're trying to have you do here. Just visually see it. It's a quarter away, so at that point, anything less than a quarter would be just fine.
Okay. My next question, unless anybody else has anything, but
No, everybody else doing homework. So
is 2.4, 137. I made an their answer was different from mine, and I'm not exactly sure how they got there. It's showing which points tangent to x is discontinuous.
oh, okay.
So
It's 130. What's the problem here? 2.4.
2.4, 137.
137. Okay.
And I think it's the k is whatever, but I can't really remember how to do that.
Okay. And it's this function right here. H of x is equal to tangent to x. Classify any discontinuity as a jump continuity, removal. So you've got a trig function in our hands here, and I don't like this pen, so let me change it up to a different one here. All right. Tangent 2x. So this one you do have to go back to your trig days. Long time ago. And so we're going to figure out the graph of this guy.
Okay.
And so there is an algebra way of doing it. It's a little more complicated, tedious. We can see it if need be. So do you remember tangent? Tangent was this little fun part.
Or was that -2?
And negative pi over 2, and then it just repeated itself.
Yeah.
So we already understand that is going to be
Yeah. If it was just tangent x, then I would say every multiple around 2, right?
yeah.
So I need tangent 2x.
Tangent to x. So now let's see how this works here. So for me to get here, right? This guy, back to the trig days here, the 2 actually scrunches things down or expands things. And so for the horizontal piece, it actually scrunches things down. So notice that if you had a 2 here, if you put in a 1 pi over 4, right? Pi over 4 multiplying by 2 gets you to pi over 2.
Oh.
So everything is scrunched down by a factor of 2, or we can say we just divide this by 2. Divide this by 2.
Okay, so it's every multiple times.
Yep.
Okay.
Divide by 2. There it is. So now that changes into that right there. That's cool. There's my graph. You know it's going to repeat itself forever and ever. And then talk to me about the answer back of the book. What do they say?
They have the let's see, it said x equals 2k plus 1 times 4.
2k
Yeah. A
plus 1.
0. Yeah, it's just weird doing last year, isn't it?
Yeah.
Do I have to say it that way, or can I just say every multiple?
Every multiple of pi over 4, just fine. Only I'll let you go with it first, and then we'll take a look at it here. So the reason why they're doing that is because of this right here. And write down that answer first, and then we're going to modify it just a bit, okay?
Okay.
Okay, so now let's take a look at the graph here. So this guy's 0, is that right?
Yeah.
This guy's pi over 4. This guy's going to be pi over 2.
Okay, so we have it. Oh yeah, that's right.
But technically this is 2 pi over 4, isn't it? Here's your 3 pi over 4. this would be 4 pi over 4. This little notch right here would finally be 5 pi over 4. That's a little problem. So is it every multiple of pi over 2? No, it is every... It's every odd multiple of pi over 2. Pi over 4, sorry. Is that good? So that's where they get this. That's why they get this K of. That's why they do this right here in the answer. So you can write down, in English you can write down every odd multiple of pi over 4. You're done. Because that will get you what you need.
Yeah, that's not. That's not very technical.
Okay, so then let's go to the technical piece here. The technical piece would be x is equal to, right, pi over 4k, right? And then you just say where k is an odd number. Right? That would be a way to do it. You
Yeah.
define k and you define the
Or
formula.
I could just have what they said, which is the I-1 or whatever. So then it's.
So they notice that they still have to define what k is, right?
Yeah.
They have
But
2k.
they didn't have k as all integers. They didn't have or they didn't use one.
There's something that looks like this probably, right? 2k plus 1,
Yes.
right? And then they still define k. Notice their formula is just a little different.
Yeah. Because they want to have all values of k, so then they. Right.
Well, they write it like this right here, where k is an integer, right?
Yeah. But then.
But you can define k to be an odd integer.
Okay.
That's it. It's not a major difference there.
Okay. Nice. Oh yeah.
Cool. Okay. Good. This is good. And the rest of you as well. If you come up with something you're really stuck in, please ask me. Okay.
So 169.
Which section?
This is 2.4 again.
Okay.
It's those application problems. I get confused
169?
a lot of times by the application problems.
Sure. Sorry, so you just put it at 169?
Yeah. And if you just, I don't necessarily need to be told how to do it.
Sure.
Just sort of put on my right.
Yeah, instead of making the force of 0 to r, instead. Let the force be protons, whichever magnitude charge. It's a scalar form of Coulomb's law, which describes the electrostatic force between 2-point charges. So here's your equation. All right, get into physics. Okay, physics people, have you guys seen this formula before?
We haven't done anything with absolute.
Okay.
What's it for?
Sad.
It's the electrostatic force between 2 charges. Okay, sorry, not physics, chemistry. We're going into chemistry here.
It's probably, no, but it's the magnitudes of the chart. And it's probably like mixture. We definitely did not do that in chemistry. Our chemistry
No.
class was very elementary.
Yeah.
It's high school. See, I'm thinking college. I don't think we did that in college either. Not intro to chem.
Yeah.
This is later on.
If you just look compare our chemistry class, like the level we are in our class or biology class.
Oh, really?
But anatomy is so hard, so. Okay.
Yep, I'm thinking so. 169 here. 0, making the force 0 at r.
That was on the two proton. Do they both have a magnitude charge with that number, or is it together multiplying? You multiply them already.
Assume 2 protons, which have a magnitude charge of and the resistance. Let me put this together. Is there a value r that can make the system continuous?
2.2 is so tedious.
0.2
these tables?
I somehow, when I was commuting, like I had made a mistake. I got a bunch of them wrong. I didn't really see my
I had it in degree and it didn't work.
Okay, instead of having force 0 and R, let me go back to what capital R is first.
Oh,
Some
yeah,
of the calculation model may be interacting particles, some threshold value. Yeah, I chose this. I thought it was gonna be fun.
Wait, but R is not greater than R is equal to R. Wait, is the little r just equal to R in the first one, big R in the first one, or are they always physicists?
That's what I'm trying to find right now here. So 168, there it is. It's the problem for 168. Simplify the calculation of model with many interacting particles. After some threshold value, R is equal to R.
No, that's
Capital R.
268.
We approximate F as 0.
So what is big R? Because little r is distance, but what is the big R?
Yeah, so with many interacting particles, after some threshold value, little r becomes big R. So if there's a whole bunch of different things, so R measures the resistance between two particles, right?
Yes.
So big R comes in when there's many interacting particles at the same time. So then you are really just trying to account for all the forces that are electrostatic forces that are being put together here. So I wish they actually just gave us the formula itself here. Okay, so it says this. It says if this guy becomes R, what happens is the force themselves becomes 0. And so explain. So after little r, when little r reaches big R, when there's so many interacting forces, we approximate F as 0. Okay. Explain the physical reasoning behind this assumption.
But
What is
that's
the
not,
force
I don't
equation?
know that one.
Yeah.
Did the next one, but yes.
We got to figure out.
Figure out.
Evaluate the force using both Coulomb's law and our approximation. So explain the physical reasoning behind this assumption.
Wait, so when there's so many, how is there no force?
Okay, about the force using Coulomb's law and our approximation. Let me just read through 168 real quick here. Assuming 2 protons with a charge magnitude of that, and the Coulomb's resist constant that are 1 meter apart. Also assume that R is less than 1 meter. How much inaccuracy does our approximation generate? Is our approximation reasonable? Is there any finite value of R in which the system remains continuous at R? Instead of making the force 0 at R, instead we let the force be. Okay, so now let's go on to 169. So the force is this. So instead of it being exactly 0, right, you've scrunched all the.
Oh, okay, so when little r is not quite as big as R, or maybe it is the same thing, then the force is not actually 0, it's such a very small number. And then what are we trying to, we're trying to figure out what's the value for R to make the system continuous? And so wait, so the magnitude of the charge of the protons, is that what you put in for Q1 and Q2?
I believe so, yeah.
Did you put it in twice, or is it already multiplied? Like, did you put it in 1.62?
I are the magnitudes of the charges of the 2 particles. I think you put it in twice. And the Coulomb's whose constant is in there, is there a value of R that can make the system continuous? If so, find it. This fun little puzzle. Sadie's like, no, I don't agree with you, Mr. G. This is not a...
I'm confused. Okay. So do I just need to, so do I change R on R squared on the bottom for R to try to solve for it? Is that what
Yeah, so you got little r here, and it's r squared in here, right? And so then we're looking at values that are, little r is greater than big R.
Oh, hey, okay. Little r is the distance between the particles. What if the world is big R? You said there's lots of particles?
Yeah, big R is multiple particles. So with little r, it's just two at a time. Little r is the distance between the two particles.
Big R is the distance between a lot of different particles if you're trying to take into account more variables or more particles.
So let's see if this makes sense here. Let me say it, see if this makes sense. So if you have two particles, we can calculate this. This is no problem. The force of charges. If you have multiple particles all flowing at the same time, I think the force between those two particles are so little that it doesn't affect the system anymore. If that makes sense. Does that make sense? That's what I'm kind of thinking here. So this becomes our variable on the bottom. And so if I multiply these guys and take the absolute value of it here, let's see, 10 to the 19, and then 10 to the negative 19 again. I mean, with a multiplier in front here, I'm kind of just guessing here a little bit here. Negative 38 is on here. And I'm just thinking about discontinuity. What would the discontinuity be? And so if you stretch out, take the absolute value of that, and that's going to be a small increase number. Essentially what's happening here is this right here, is you're going to divide this into here, take these guys, divide it into there. So you're going to have a constant right over here. And so...
Yes. So, okay, I'll divide it. So then I'm going to end up having R squared on one side and then 1.6 whatever times that absolute value divided by 10 to the negative 20 times 8.98 times 10 to the 9. And then I'm just going to solve.
Sorry, even better yet, how about this? How about we take all this on the right-hand side, and we multiply the r squared over here to the side?
Yeah, that's what I was.
And then divide that. So we have an r squared that's equal to all this number here. So the question is, and r squared is going to be, and take a square root of it. You can do that.
Oh, and actually, you know that.
Okay, and r is distance. So then, something, is there ever going to be a zero value here? That's the question.
Wait, where were we talking about?
Yeah, so,
I didn't see where you're putting this.
sure. So when you do a square root of this, right?
Oh, yes.
So let's go back up here. This is kind of, I think, the crux of it, because we're not generally just dealing with the numbers themselves, we're dealing with the formula here. So notice this guy's R right over here, right? And it's equal to 0.
Wait, isn't that 80 or
That's
F?
60.
Isn't that F?
That's F,
Yeah. Okay.
So it
That's
says,
the 0, yes.
for 168, it says that
force, we approximate the force to zero.
Yeah, little r is equal to big R. So if we do that, you multiply both sides by a big R, right? Technically, divide by 0, right? And there's our little problem. Is that the way you get 0 here is because you have a 0 at the bottom, or almost a 0 on the bottom. Now, if you're approximating it by not by 0, but by this guy here, 10 to the negative 20, you don't have yourself a 0 yet.
Okay, so. Okay. So, what am I supposed to be? Is there a value that? So if I solve for it, then it will work since I'm using approximation of math that's not 0.
And we're looking at this here. So if you make r smaller and smaller, as you got this right here, right? Little r is the biggest big R could be, okay?
Yeah.
So how could you make little r go smaller? What changes here to make r smaller?
You make h bigger or f bigger, the force bigger.
Yeah, let me just jump to this here. So if I bring this down here,
Yeah,
it's 10 still to the negative 20, correct?
yes.
Because I've divided it. This is 10 to the negative 38. This is 10 to the 9th here. So as I bring this down, this is 10 to the positive 38.
So it's 10 to the 38 times 10 to the 9th.
Approximately, yeah. Not
Divided by 10
exact
to the
values.
negative 20. About.
I am looking for. See, I think we're stuck on this one. Do you have another one? We'll come back to it if need be.
Yes, I have.
Okay. Let me ponder that for a little while. Let me just see. What is the answer to it, though? What does it say?
It's like 0. 0, 0, 0 something.
519. So they actually found a value where it would be, well, there's a discontinuity. Okay. So what value would make this a discontinuity?
Well, are we supposed to be finding a value that can make the system continuous? Where it's not a discontinuity? Yeah. Aren't we? Isn't this problem though supposed to be finding the value of R that can make the system?
That can make the system continuous, yes. If so, find it.
So,
I'm going to have to take a look at that.
okay.
I thought it'd be a fun one. It is a fun one. It's a little
Yeah.
challenge here. So let me think about it a little more.
These problems are always fun if you can figure them out.
True.
It's not necessarily the given.
Okay, so in my intro to math proofs, no, my second class in math proofs, we were given this. There's a math journal for undergrads, and it's pretty much kind of given at the bachelor's degree level, right? And there's problems on there. There's like I think 6 problems per journal.
Oh, you're like trying to solve them.
That was it. Our grade was dependent on if we could solve them. And so we had groups of 4, and it was okay. He got the math journal for August, and he's like, if you guys can solve it, you can only choose one. So you have to choose a problem without understanding the problem whatsoever.
Can you solve it?
So August, September, October, November. You got 4. If you solved all 4, you got an A.
Oh my lord.
You get a B, a C. If you only solve one, you get a D, and if you didn't solve any, you got an F. That was the class. That was it.
Wow, that's pretty.
Yeah, that sounds amazing. Also super
Uh-huh.
hard.
So
Did you solve them?
we got an A out of the class. It
So
was
you
crazy.
had teams though. That helps.
It was just for the class, and it was randomly selected. So you just put you, and you together.
Did you have to go to classes, or is it just the problem?
So as we were going to classes, we would talk about different techniques. It may not necessarily for proofs. It may not necessarily apply to your problem. He just gave you, his lecture was on techniques of solving math.
That
proofs.
sounds really cool though. If you solve a proof, you're very, it's a good feeling.
Yeah, so you got your name on so the next month's journal, it would say who solved it, and then the answer, the solution answer to it, and then here's the next one, sort of thing. It was crazy. That was a crazy class.
Stuff like there's problems they have. I don't know where it is, on their website, some professor will show a really hard problem. But I don't know.
Okay, so there's a challenge. I'm going to dig into that challenge here. But what is the next one?
Oh, so this is sort of a stupid question, but on the review exercise, whatever.
For 2.4?
No, for 1 point, for 1,
Chapter 1.
the review. 315, I was trying to graph it using the things that we did in positive transformations. And I kept on getting it wrong. I'm not exactly sure why. I'm probably just being stupid, but
I know, let's take a look at it here. Oh, this is so fun.
it's just, X.
It's the review itself, though, right?
Yeah. It's over 1, or 315.
Oh, wow. Okay, let me check.
That's kind of fun. Well, just, X is fine. It's the same thing. It's just right. I think theta is when you're using.
Well, I was trying to graph it,
Yeah, you can use
and it
X.
still puts in X.
It's the same difference.
I know, but I wanted to see theta because that's what the problem says.
When does it automatically says theta? Is it when you're using like parametric equations or something? Is that what it doesn't say?
Theta for your variable?
He wants it to say theta instead of X, like isn't it?
Yes.
Yeah, but it's
So you can't choose what it is, it just has one.
You go to mode
parametric
and,
is
and go to mode to see. I forgot what it was here. Parametric equations would be T.
yeah, T.
T is parametric.
So function would be
Theta
X.
is
Polar.
theta is polar.
Polar, that's right, yes.
Why would you want that? Just graph normally. That's
But I like that theta because the problem says theta.
only you had it in your calculator.
But it's a different system, though. So it's polar coordinates, which is a different measurement system. That's the problem.
Polar coordinates are
What did you just say? First I do e to the x, and then I flip it over, and then I do the transformations like to the right and left above. It was the way it looked did not show the right domain.
But find the state the domain and the range for the given problems here. So as far as given problems here, so this is 305. This is the review for chapter 1, correct?
Yeah.
Okay. So ln function normally you just do ln of x only, right? It's going to go like this. It's going to go
Yeah.
right there.
Because
So
it's like e to the x is up, and then LOX is reflected over the diagonal.
perfect. Yeah. So it's defined from 0 to positive infinity.
Yes.
In this case here. So with that little -5 in there, that's the only thing we've got to account for. So if you This is transformations from algebra 2, right? So if you're subtracting 5 from x, that piece there is going to go to the right.
You know, yeah, that was a really stupid mistake. I think what I did is I changed it to ln of negative x plus 5, and then I felt like I had to flip it again. Yeah, that was stupid.
That was just, it just moves. Horizontal transformation.
Okay.
Cool.
Thank you.
Uh-huh. Okay. I'm also liking this.
Let's see.
Equal 0.
You like it okay?
It wrote down that I was going to use about 3. I got it for why.
Okay.
Oh yeah, I thought I understood it, but I got the wrong answer.
Okay.
Like a paragraph.
2.3103. Following example, use direct substitution to obtain an undefined expression, then use the method of example 223 to help determine the solution here. So if you plug in -2 to that, obviously you get a 0, is that right? Okay, so then the rest of it is going to be, I think you're going to factor it out. You're going to have to factor it out.
Yeah. So, I think
Maybe it was just the whole concept of a one-sided limit. Maybe that was it, or no?
I factored it, and I got on the top, maybe I just factored it. 2x minus 1 and then x plus 4. And then
2x minus 1x plus 4.
and x plus 1 and x minus 2 on bottom.
Gotcha. Okay, let's see.
And then then I thought since -2 plus 1 is not 0, and -2 minus 2 is not 0, I can do it. So I did it, and then I got the wrong answer.
Okay. That should be a +2 right there.
Oh, definition. Okay, so
So let me change that, because that's the problem area right here. That's the one that's the
now I need to.
issue.
Okay. So now I just need to let's see.
Okay, let me check the top here. Let's see.
So
That's
you know
2x
how
squared.
to-
That's a minus that.
Then 1 second, so I didn't know if I did it.
Okay.
So I'm trying to think what law or what technique to use.
I'm looking at 2.3 real quickly here. Evaluate the limit in the form of KO. Yeah.
Oh yeah, it said use the method of 2.23 that I was going to use.
Yeah, this is the long way around here, but here's essentially what you want to do. When you plug in a 2 into the top, do you get a 0 or not 0?
Not 0.
Not 0. Okay, so if that happens, you have yourself this little problem. Or you have yourself this little problem. I should start with that, right? So the question really is, are you going to negative infinity or positive infinity? That's the only issue there. And this exercise there, they try to pull that little piece out of it to say that's the problem. But you can sort of think about this is going to be very little, and the question is it negative or positive? It's coming from the -2 from the left-hand side.
So if it's -3 plus 2, it's
Sorry, maybe do this. Let me just do it kind of like the book here. So this is right here. You pull this piece out by itself, and then the limit as x goes to -2 on the left. You could do the other ones by plugging them in. That's essentially what they're saying. And then we're going to do, and we're going to determine whether it's going to go to positive infinity or negative infinity. And again, it's because of sign changes, right? It's because of sign changes that are going to happen.
so
And it's all about signs. We don't care about anything else here. So this little guy here,
all about signs. Okay, so if it's negative, as you approach from the left, you have negative numbers until you get 0.
as you approach from the left, not necessarily, because you have these little multipliers that are on top. So let's just do
You guys put the whole box.
yeah, it's this whole
Yeah,
piece
okay.
here together.
Wait, so
And so
that like we were doing in class.
yeah,
Yeah, we
and
did
then
that in class. And we one
I think we did something like that, yeah.
Okay.
So you have this guy here, you have a -2 approaching x plus 2 from the left side. Right, so you're at -2.1, right? -2.001.
What are you looking at?
Sure, I'm looking at this piece right here. And just
Oh, just that
determining,
piece.
determining if this guy is going to positive infinity or negative infinity because of the signs.
Negative.
I'm going to go negative infinity on that one, right? Negative infinity. Okay, now, the other issue is that you have signs over here too.
Yes.
So for this one, what we do is we just plug in the values. So I'm going to plug in the -2 into there. -2, it will give me a -3, is that right?
-4 minus 1. Well, it's still negative. Wait, is it plus 1?
Oh, minus one. Sorry, I wrote down a minus. I wrote down as a plus minus -1. -5?
Yeah. Well, it's still negative. So yeah, it's
Yeah,
negative.
negative.
And then negative equals source. So negative and positive on the top, and then negative on the bottom with the x minus 1.
I have a question. What is the difference between the closed dot and the open dot? I always get them confused.
Sure, yeah. Closed dot means it's part of the answer, so f of that gives you that value.
Okay.
Open dot means the value is not there.
Okay.
So, say you good negative on the bottom, is that right?
Yeah.
And then on top, negative. Yeah, I've got a positive. These negatives will cancel.
Yes.
So then we're looking at a negative infinity times a positive value, so it still stays negative infinity.
Yes. Okay. Yeah. That makes sense.
Okay, so we grab the infinity out of the group and determine which sign it's there. Then the rest of them are just plug-in values, and the only thing we care about is the sign inside.
So we know that, just to make sure, we know that the x minus or x plus 2 is going to be negative infinity because -3, you're going from the left. So it's
Yeah,
negative.
and those you got to think about differently than those because you're thinking, okay, which way am I approaching? Because if it was from the right-hand side, you'd be at a -1.9, right? And if you add a 2 to it, then you would have been still at a positive infinity. Are we good? Sorry, just want to make sure you understand. So if we were approaching from the positive side, right? This would have been a positive infinity of them.
Yes.
These guys would still be the same.
Yeah, but then it's I get that.
So then we know if you approach from the right and from the left, we know that we have a split direction here. From the left, it's going this way. From the right, it's going this way. So at least we know that.
Yeah. Okay. That makes sense. Yeah.
Split direction. Okay. from Algebra 2 and even trigonometry. Do you remember split direction and same direction? Because these are my factors, right? So I know in this guy, I already know this right here, just based upon factoring this out. I know this, and I also know this.
I think we did that, but I can't remember.
Okay, and then I know my zeros are at -4.
Oh, yeah.
I have a 0 over here. I have also a 0 at 1/2. So that's 1/2 is like right here, right? Before -1. Then I know I have split direction. So that I know I have something that looks like this. Then I know that I have something that looks like this. And then this needs to be modified to look more like that. And then notice these guys. Remember that from Algebra 2? Is you can determine your horizontal asymptote based upon your leading terms.
Oh, yes.
So-
I was never good at that.
Okay, so then my leading terms are 2x squared and x squared, so therefore I know this as well. So now I have a little graph here on my hands.
Wait, was it like for if there is no coefficient, then because I can't remember the rules for I remember that we found horizontal asymptote that way, but I never had to memorize them, so I didn't.
So for horizontal asymptotes, you just look at your leading terms.
Yeah.
And you chop these off and you look at the ratios of your
So if
coefficients.
the top, if the numerator is bigger, then it's what? And if like, can you remind me of that?
No, that's oblique asymptotes. If the numerator is greater than 1 right here, then what you have to do is you have to do long division, divide this into this, and that gets you your oblique asymptote, like that. If they're both the same, you have yourself a horizontal asymptote,
Okay, yes.
and the coefficients are your horizontal asymptotes of y. Y equals 2.
Okay, yeah, I remember.
And then if the bottom is bigger, then you do have a horizontal one, and it's y equals 0. There's your sort of 3 different possibilities.
Yeah, why do you know that?
So we were just looking at this guy right here. That's what we found out.
Yeah, but do I care about that for this?
You don't care about the function, the whole function thing.
Okay.
You care about just the fact that you found it.
So many things.
I just want to connect that to algebra 1 because it's really you're just looking at a small little tiny piece there. All right, you guys have another question or no? Are you doing okay?
No, yeah.
Okay, I'm gonna finish early just so Ms. Bear can come in and get her stuff set up all the time because I feel like I'm always in her way. So I'm gonna finish the